colors are light of different energies, so it's about spectroscopy. And over next 45 minutes, I'm going to give you a very short, of course, very chaotic and very biased introduction to optical spectroscopy. And we'll start with answering a few questions like what, why, and how we are doing optical spectroscopy. Then I'll introduce several techniques: frequency domain spectroscopy, Fourier domain spectroscopy, and a bit different topic on Raman scattering and photoluminescence. We will review some CW optical setups at MagLab, and I'll introduce your lab practicals. Optical spectroscopy can be defined as a probe of interaction of matter with light or photons. And of course, it's about, first of all, energy, but light or photon has other important characteristics. Momentum, which also includes direction, so we can study anisotropic materials. Polarization, it could be linear or helical. This would access, again, polarized properties of matter, or with circularly polarized light, one can access spin degrees of freedom. Intensity or flux. In respect to this quantity, one can define linear and nonlinear optics. I will mostly talk about linear optics, like if you take the analogy with resistivity, it's like Ohm's law regime. And then there is, of course, a time scale and very short length scale that will be partly covered by Steve McGill in the next talk. It's a domain of the fast optics. And so we measure the spectrum. It's a response of your specimen to electromagnetic radiation as a function of energy. And photons has a huge span of energies, going from many electron volts to micro electron volts. Or rather in wavelengths from nanometers to kilometers. What we define usually is optics. Visible, not at all. Visible is just a very small subset of optics right here. A right scale for optics in condensed matter is the lattice parameter. When the photon has a wavelength close to the lattice parameter, we don't observe internal properties of course, we observe internal properties, but it's mostly diffraction, just given by the lattice. So we start somewhere from that scale, considering optics. On the other side, when we go through UV, visible, near-infrared, infrared, terahertz, microwave, then it's radio waves. And that's a meter scale. And it's just hardly possible to study in the lab objects of a meter or kilometer scale. It's a radio wave domain. So we are talking about something from microwave to ultraviolet. That would be our region of interest. And one can employ different scales to create a spectrum. And it could be energy, wavelength, frequency, even temperature. Probably the most frustrating unit for a non-spectroscopist is a wave number. It's just 1 over lambda. It's very commonly used and very unusual for non-specialists. Just to be memorized, that's it. The change of energy by 1 millielectron volt is equivalent to the change of frequency and wave numbers by 8 wave numbers. And it has its origin from the very early beginning of optics history. Of course, it's very natural to express from absorption coefficient in something like 1 over length. Then the dispersive spectrometers and the lenses, it's also to describe the operation. The formulas finally translates in something 1 over length. But of course, it's all the same. It's just a question of the habit. And the spectrum, so as I said, is a response of matter to the radiation. And it could vary a lot. For me, this is the most important spectrum for the human history, for the life history on Earth. That's a spectroscopist's take on the life development on Earth. So this shows the penetration depth into water of light. So let's say inverse absorption. And as you know, long time ago, there was a lot of heavy photons bombarding Earth. So the early life was protected by proto-ocean. And indeed, say, like UV light, very heavy light, it can just kill everything. And Florida is notorious for UV light. But it's enough to put like 1 millimeter of water to absorb almost everything. It's perfectly protected. On the other side, it's also absorbs very well. And there is a very narrow region right here in the visible light when the water is very, very transparent. And that's what allowed to develop through evolution photosynthesis of visible range photons. In many senses, it will be much more efficient to absorb UV photons because it's higher energy, it's more efficient. No, because of this. That's the history of the photosynthesis. And then it comes closer to animals, that's about vision. Also, vision was developed in early creatures in water, and it's also focused on the visible range. In condensed matter, we use optics to probe various structural, electronic, or magnetic states, bands, or excitations. This is the diagram taken from the review by Dmitry Basov, and I won't even pretend that I know all these types of excitations. Just to give you a whole panorama of what could be covered optically in this region. And once again, it's a very narrow range of visible optical spectroscopy. Of course, you cannot cover such a whole range, such many materials with just one technique. And there's a very big difference between optics and maybe measurements of transport properties, like resistance, magnetization, or heat. You have to apply different things and always keep in mind the big picture. If not, you can enter something like this. You don't know, if you focus just only on one side, only infrared, only Raman, only high energy, you will be just talking about only one subset of your system. So it's important to look globally, okay? And believe it or not, but spectroscopy and high magnetic fields are very lovely alliance. Because of the similar energy scale, because of some internal properties, like they both have the same properties in respect of time reversion symmetry. And I just want to remind you few energy and length scale associated with magnetic field. Of course, the electron subjected to magnetic field starts to circulate with this characteristic length of the nanometer scale. And this corresponds to the cyclotron energy of about, for many solid state systems, let's say semiconductors, of about 1 millectron volt per Tesla. Zeeman energy associated with spin degrees of freedom. Then interaction energy scale, where it's the ratio of the Coulomb interaction over magnetic length. And also time reversal symmetry. So magnetic field is created by current. So current goes this way, and it creates magnetic field like that. If I reverse time, that means current flows now that way, and magnetic field change the direction. I can do the same about light and circularly polarized things. They measurements with circularly polarized light of different helicity allows you to emulate breaking of the time reversal. Very important feature for magnetospectroscopy, maybe unique feature. What else could be done with magnetic field? The dimensionality of the system. If one starts with three-dimensional system, like three-dimensional electrons, and reduce it to, and apply external magnetic field, what essentially happens with the density of states and electronic state will reduce the system effectively to one-dimensional like, with these spikes of the density of states. And because there's only 1 degree of freedom in plane for the electrons to rotate or to have the energy quantized. And if we start with two-dimensional system, we effectively reduce the system to 0D. It's only about energy and relaxation. Of course, it still stays three-dimensional system, but very powerful experimental tool as well. how we do conceptually optical spectroscopy measurements, conceptually very simple. Shine the light on the sample and measure what is going through or going back. And there are two types of spectroscopy in general. Broadband spectroscopy, when you measure exactly at exactly the same frequency the light coming back as you shine on the light. It's like absorption transmission or reflectance measurements. Those are broadband spectroscopies. Or you can do resonance spectroscopy, when one excites the system with a well-defined, usually very intense light from a laser, and then measure scattered light. It could be scattered by some states inside, like phonons or collective modes, and that would called inelastic light. We will call this inelastic light scattering or Raman scattering. Or one can excite system into the high energy levels and measure photoluminescence. You can also combine optical spectroscopy with electrical technique and study photoconductivity spectra or electroluminescence spectra or electrical field modulated reflectance. All this is fine. And of course, we add other external parameters like magnetic field or pressure or temperature or doping, either through chemical substitution or through electrostatic effect, like gate. Okay. Yes, and yeah, this is the simplest sketches of these two types of experiment. Broadband, take a broadband source, send it through the sample, and measure with the broadband detector. The reflectance is the same. For excitation, it's a laser, single line, and broadband spectrometer. To get some information from broadband spectroscopy, we do something more, like take a reference spectrum. Your spectrum measured by the detector, it's a convolution of everything. Spectrum of your source, spectrum of your environment, spectrum of the sample, and the spectral response of the detector itself. When one looks, and you will see this at the lab practicals, at the raw data, usually you don't even see at all any useful features. They're all hidden. All what you have to do is to remove the sample and measure the response of the system, and then take a reference. That's referencing. And transmission, of course, is good for more or less transparent samples, like insulators, semiconductors, or very thin film of conductors. While reflectance spectroscopy is rather implied for good conductors, or study something highly reflectant like a Australian band of phonons that we also will study during the lab practicals. You will see how strong could be reflectance from a transparent material. But it's also not, of course, just about measuring a spectrum. We want to deduce some microscopic information about what is inside. And let's consider a simple sketch of the system of several energy levels. Ground state and low energy state usually split due to vibrational degree of freedom or spins. And this is characteristic energy of millielectron volts, maybe tens of millielectron volts. And then there are high energy states. It could be high energy electronic bands or states or impurities. So in a broadband spectroscopy, again, we shine light like everywhere from millielectron volt to many electron volts. And when the energy of the photon coincides with a loud transition, for example, like this, we will observe a minimum in the transmission. And that's your characteristic energy. And line width, if it's a homogeneous sample, then the line width provides information about the lifetime and the density of states. Then as we increase the energy, maybe nothing else happens, it will be just transparent. And at some high energy, we start probing high energy transitions, like this E1, let's say some generic impurity or some generic ground state. And we will see it as another well-defined minimum. Of course, the band would appear as a well-developed feature. In excitation spectroscopy, we do something different, but we can probe same physics. So let's consider photoluminescence. For photoluminescence, one shall excite well above your region of interest. So this is the excitation from the laser, somewhere well above. And then one lets the carriers, the electrons, to relax. A lot of way of non-radiative relaxation. One can emit usually, the most efficient is always emitting optical phonon because they have high energy. Emit one phonon and you can relax by 30 or even 100 milli-electron volt. It's a very fast process. So it could cover really big energy. Then it also can relax in the lower scale through acoustical phonon emission. It's a milli-eV scale or less. So it has to emit a lot of acoustical phonons, and this is a long process. But finally, you have certain population of electrons on lower-lying levels. And if symmetry allows, if the dipole allow transition, they can recombine, go back, and emit light. That's called photoluminescence. And spectrally, if this is our energy of our excitation laser, we will observe bands on the lower side, on the red side from the, in respect to the excitation frequency. So those are PL bands. And again, the energy corresponds to the energy separation. The line width reflects radiative lifetimes and density of states. There is another process called Raman scattering, inelastic light scattering. We'll talk a bit more about this, but that's the process. This process goes through some virtual state. Raman is always forbidden in the first order, unless it's resonant Raman. But let's say usual Raman process is forbidden in the first order. It's second, third, fourth, etc. And then this, say, electron promoted to this virtual state relaxes back to the final state. These two states are real. That's what we want to probe. And in the Raman measurements, one can observe two lines in respect to the laser, Stokes and Ita-Stokes, red side, blue side. They have the same energy separation. They should have the same line width, but different intensities, because one corresponds to the absorption of this energy and another of emission. So these are two most prominent examples of the excitation spectroscopy. And again, this could be used for the variety of purposes, not only physics, but chemistry and biology. I think at least half of our users of Raman spectroscopy come from chemistry. Why it's so good for physics and chemistry, particularly Raman spectroscopy and infrared spectroscopy? It's a very sensitive structural probe. It follows very strictly selection rules, because IR activity is related to the dipole transition, just the displacement of atoms which produce a net dipole moment. And that's how it can be detected with light. Raman activity is something totally different. It's about polarizability of an atom. And it has a very simple rule of mutual exclusion. So in a centrosymmetric system, a vibrational mode may be either IR active or Raman, but not both. And by doing polarization results measurements, you can deduce in what direction, in what direction happens this movement of atoms. Let's say simplest example of the CO2 molecule. It's a symmetric molecule, right? And the very strong vibration is like that, totally symmetric stretch mode. No net dipole momentum. Distribution of charge stays similar, so it's IR inactive. But it has a huge, big change of the polarizability of this atom in the middle. So it's Raman active. On the other side, asymmetric stretch is IR active. We indeed have now a distribution of charge here, and it can be probed with IR spectroscopy, but not with Raman. And the band of this kind, they are IR active but weak, simply because this displacement of charge is very small compared to that one. And again, we will measure very easily this particular CO2 stretch mode during the IR lab practicals. Calculating selection rules, could be difficult, especially for people who are not doing Raman spectroscopy every day. And I strongly recommend you, for this purpose, to consult first the site of Raman Spectroscopy at Bilbao Crystallographic Center. It's kind of a Bible for Raman spectroscopists. It has a lot of online tools. You just work on your system online. And there are also some tutorials there which explains terminology used in Raman. For example, what are these meaning of the optical phonons, A, B, etc. So the letter C is reserved for the principal rotation axis. That was an agreement since a long time. So A corresponds to displacement along principal axis other than C. It's a linear polarized. B will be another linear polarization. E corresponds to doubly degenerate modes in plane. T for triply degenerate modes, and these indices also indicates certain symmetry, rules of symmetry. And let's take as an example aluminum oxide or sapphire. We will study this material at the lab practicals. And let's say you want to calculate the allowed Raman and IR modes. All what you have to do is to open a crystallographic handbook and find the symmetry of this thing, like this. Then you go on to this Bilbao website and put here the right space group and select position of atom. Within this space group, you can populate in a different way your unit cell. And click continue. That's it. And then that's the table, which calculates for you so-called representation groups and indicates the Raman modes. So for aluminum oxide, we expect 7 Raman active modes and 6 IR active modes. We will see if you can detect this at the lab practicals, all 13. Now about techniques. I will discuss briefly 3 techniques commonly used, particularly in CW spectroscopy. It's a frequency domain spectroscopy, Fourier domain spectroscopy, and one more time about Raman spectroscopy. Frequency domain spectroscopy is the oldest one. It's in the scientific form was invented by great Isaac Newton. He did this nice experiment with glass prism that was published in 1665. And by the way, this was the very first Newton's book or article written in English. Everything before he wrote in Latin. So that's the first English scientific book. And of course, this concept then evolved for lots of applications and has lots of influence, not only in physics. For me, it's one of the greatest influences of this. If you don't know Dark Side of the Moon, I don't want to talk to you. It's fantastic. Okay. And that is kind of mathematical foundation of the frequency domain spectroscopy. Let's say we start with a broadband light source, and then we can disperse light and somehow select particular wavelength of the kind, send it through the sample. That's a spectrum of the sample conjugated with the electrical incoming light. We measure with the broadband detector, and that's the quantity we measure, that's the intensity, this is in square. We, like that, don't have information about the phase, only about the amplitude. And to recover the spectrum, we need to reference it. So divide the spectrum signal from the sample by the signal from your reference, just empty hole going through. It can be realized in different ways. For example, we can remove the actual monochromator here and use the specially resolved detector, like a so-called CCD camera. Something like this. This is the layout of a Cherny-Turner spectrometer. Incoming light comes through the slit. That's the most important thing, first important thing to determine your spectral resolution. And then it goes not to a prism. Prism absorbs a lot. It's not easy to operate. To the grating that disperses light, and then it's a multi-pixel detector. By addressing particular pixel, one can say, okay, this is that energy, and that energy. IR spectroscopy started also with dispersive measurements by Wilhelm Herschel. And we know exactly when it did happen. It did happen on February 11, 1800, because there is his logbook with exact date and even time when he performed these measurements. And this is pretty genius measurements. He still used the prism to disperse light, and that's the slit. But he moved the slit further away out of the red light. Of course, he could not see anything, but he could put thermometers and then observed peaks at particular bands, high temperature, low temperature. That's how he introduced what he called a radiant heat, or nowadays infrared light. Why I'm putting so much accent on IR spectroscopy? What is special about this? In fact, everything is special. It's a much more difficult technique compared to usual visible optics. First of all, it's about low energy photons. Usual source is a black body radiation. And black body radiation, our usual source is the sun or incandescent bulb. It has a maximum at about visible range, somewhere here. And regardless of your temperature, you go lower or higher, that's the tail, that's the infrared. And there's about 10 to 7 difference in energy of photons. And energy then transfers in your signal. So 10 to 7 less signal in infrared. Same about detectors. Detectors has intrinsically low detectivity at infrared frequencies. It's another factor of 10 to 4. So at least it's about 10 to minus 7, reduced 10 to 7 reduction of the intensity of the signal from visible light to infrared. And any thermal gradients, your hand is a huge source of IR radiation. It's 10 microns. It's right in the middle of the range. Other problems is that unlike optical glass, it does not exist, almost does not exist, materials transparent in infrared. All usual materials have somewhere bands, absorption bands. Only one material is good for infrared everywhere, for optics everywhere, it's diamond. I wish we could build all spectrometers, all windows, all things from diamond. Don't have a budget for this. Okay. And I think the most widely used and best technique for IR spectroscopy is Fourier transform spectroscopy. It's based on the microcell interferometer, which is depicted here. And let's send the monochromatic first light from the light source. It's a beam splitter, fixed mirror, and movable mirror. Then our interferogram or Fourier image of this line will be just a sine function. So if we measure accurately the position of the mirror, actually signal to detector as a function of the mirror, we can recover the interferogram. then perform inverse Fourier transform and recover the spectrum. So practically, it's not that simple. We use broadband source. So if the single line source produces infinite sine interferogram, ideally broadband source produces just huge spike at the zero path difference. So all information, spectral information, is in these very tiny wiggles all the way around. So one can measure, so we measure first the interferogram without sample, that's the red line, then put our sample, it's an example, let's say for reflectance measurements, but these graphs are absorption spectra of air, actually, and measure this interferogram. And I already can tell you, just looking at the interferogram, that we have lots of sharp lines, because we have these sinusoidal components, multiple of them. Let's perform Fourier transform. Red is the spectrum of reference, blue spectrum of your sample. You divide and you recover beautifully absorption spectrum, actually transmission spectrum of air. And all these are water lines. They are real. It's a water vapor in air. Not only just water bothers us for IR spectroscopy, but CO2. That's why the IR spectroscopy stuff has to be vacuumed. They always has to be pumped at least to about 1 millibar. From the spectrometer, all the path for the IR light to the sample and then back to the detector. So from a pure optics point of view, there is nothing special about IR spectroscopy. Practically, one has to pay lots of attention to every small detail. Timeline of Raman spectroscopy, I think it's a good, interesting history. It was predicted by Smeckel in 1923. And it's a really perfect prediction, very, very well-founded quantum mechanical treatment of the system. And in 28, two groups independently, Landsberg and Mandelstam in Moscow and Raman and Krishnan in India, observed such a strange sidebands. And they published their findings simultaneously. Landsberg and Mandelstam actually provide microscopic explanation for that, based more on classical approach, but it's still correct. While Raman first paper was just observation. We observed sidebands. Who knows what is it? And then what I would say is not very correct event, that in 1930 Raman wins alone a Nobel Prize for physics. Smeckel was not there, Landsberg Panzer was not there, not even Krishnan was not there. How did it happen? Of course, Raman merits this a lot. But he did a very clever thing. He recognized quickly the importance of this discovery and made a world tour of seminars and lectures, promoted a lot. And in like 1 or 2 years, everybody knew that it's only Raman who did it, and Krishnan does not exist, or others. And he won the Nobel Prize. So if you find something really, you believe, worth Nobel Prize, disseminate the result. Make it loud. Okay. But for many years, it was just a curiosity, a very weak signal. But history changed in 1960 with the invention of the laser. You need a strong light because it's a forbidden process. You need a very strong light. That's another interesting story. So Nobel Prize was awarded to Taunas, Basov, and Prokhorov, while everybody knew that Ted Maiman created the first laser significantly earlier. That's his picture with the first ruby laser. And why he did not get the Nobel Prize. Now it's a question about logbook. He was not very good with keeping exact trace time scale of his experiments, did not publish fast, did not promote it, and again, he did not get a Nobel Prize. So please, please use your logbooks, write everything. Everything worth doing, worth writing. You never know. Why it's so difficult to measure? Because it's so weak. So that is the Raman efficiency of typical superconductor, EBQ. And even the strongest Raman line from phonons have the Raman efficiency 10 to minus 7. That means out of 10 to 7 incoming photons, only one photon scattered inelastically. And in Raman spectroscopy, when we have signal of several photons per second, that's photons. So photons is very small, okay? You have lots of photons around. It's a huge signal. It's very easy to measure. Sometimes we have to measure 1 photon per minute and accumulate signal over 30 minutes or hours to get something useful. This implies that it's you need for Raman spectroscopy very clean sources, very high collection, efficient collection optics, and performance spectrometers. Not every spectrometer, simple spectrometer, would work for Raman spectroscopy. So now I will review a few CW magneto-optical spectroscopy techniques available for users at MagLab. Let's say on FTIR, we have 3 Fourier transform spectrometers that can be coupled to our superconducting or resistive magnets. That's a typical layout. Spectrometer is somewhere a few meters away from the magnet because it relies on the very accurate movement, and you cannot bring it closer to magnetic field. You cannot disturb this. So it's typically 2 meters, 3 meters of vacuumed light pipe to deliver light. Then it's redirected to the field center. Where's your sample? And it's like for transmission measurements, infrared light goes through the sample and then detected by the bolometer, not usually called at 4K. For me, this is the technically the most challenging experiment performed so far with IR spectroscopy. Here, it's about structural resonance in monolayer graphene. So the sample is one layer, one atomic layer, about 20 microns in diameter. And these people were able to measure not just the interband transition or CR-like transition in graphene, but also apply the gate and observe this kind of splitting of the ground state. I think it took one spectrum is about 10 hours acquisition time overnight to get such a level of sensitivity. We also do PL and Raman spectroscopy, specially resolved. So that's a setup with fiber optics. When the incoming light comes through the fiber from the laser, it gets collimated, cleaned with the filters, reflected from the mirror, goes to the beam splitter, and then focuses on the sample. And PL or scattered light collected by the same lens now goes through the beam splitter, through filters or polarizers, and then to the spectrometer. You can also install samples on piezo positioners with sub-micron accuracy and working distance of several millimeters. So we either can study microsamples or several samples at a time, not at a time, in one load. And these techniques, these two techniques are available eventually with any magnet, including 45 Tesla hybrid. As an example, I choose the work on excitons in monolayer transition metal dichalcoyanides. It's a good example of really micro PL. That's the sample, 3 micron. This is small flake, again, atomically thin. And it's like 10, 20 meters from you in the field center of the magnet at 1K, 3K, 0.3 Kelvin. What we did here, we studied the optical properties, excitons. This material has a kind of motif of graphene. We recognize these hexagon structures, so it results in this brilliant zone. But unlike graphene, with only one sort of atoms, here we have 2 atoms. So they are not equivalent, these 2 valleys. And I would just say that because of strong spin-orbit coupling, these valleys are not equivalent in respect to time reversal. And as a result, they can be accessed selectively by circularly polarized light. If I shine like right polarized light, I only probe K valley. Another valley will be silent, and vice versa. So it's maybe the first working example of Wally selective optics, which may be one day would result in so-called Wallytronics. And we probe excitons in these systems. Exciton is an electron-hole pair bound by strong Coulomb interaction. Like this, it's kind of analogy to the hydrogen atom. If there are enough electrons, even more weird creatures can be bound, like tryons, 2 electrons in one hole. And in these materials, one can find all very, very many possible combinations. How can you form exciton from here to here, from here to here, and even more for charged excitons? Not all of them are bright. Some of them are forbidden for emission by the selection rules. So a big question, what is the ground state? What are the ground states of the tryon? What is the ground state of the neutral exciton? What is the radiation rate? And magneto-optics is a very good tool to do this. These are PL spectra measured from -30 to +30 Tesla on 2 materials. They have a linear shift, which is due to Zeeman effect. That's OK. But the change of intensity is very different. And if one analyzes the change of intensity of a field, one can conclude on this ground state of these tryons. They're very different, fundamentally different. In this material with lighter atom, it's intervally tryon. In all materials with tungsten, that's our intervally tryon. And of course, we do a lot of Raman spectroscopy with chemists. Another example of Raman studies up to 35 Tesla at low temperature. And just few words about your lab practicals. So that will be about aluminum oxide. If you dope aluminum oxide with titanium or ferrum, it will be sapphire. It's not your sample. OK, if you mess with chrome, it will be ruby. It's not your sample either. We will do, sorry, very boring synthetic sapphire, pure one. This will be your sample. And as I show you, if you run the symmetry analysis, you can find all the phonons. So it's 5 atoms, 2 groups per unit cell, 10 atoms total. A priori, you would expect 30 phonons. And we can discuss why it looks like it's less than this. And this is kind of spectrum that I would expect you to measure during the lab practicals to find all these phonons from a piece of aluminum oxide. What about IR modes? There are 6 of them. Simple way, let's measure transmission. We should see it, but we don't see anything. You won't see anything. It will be just, it's called a Australian band, forbidden band. Nothing happening here. So the right way is to do reflectance. If you measure reflectance, you see huge change. That's due to the phonons. And all this, in this geometry, we measure only 4 perpendicular to the plane. And that's 1, 2, 3, 4. And finally, we measure photoluminescence, very different scale of energies. Even in the pure sapphire, there are still few, maybe 10 to 12, 10 to 15 chromium impurities. But that's enough to induce a huge, huge PL. OK, so I'm going which way? It's time to summarize. So we discussed principles of optical spectroscopy, have a look at TCW instrumentation, and I'm eager to see you performing well at lab practicals. Thank you.
There is an asymmetric unit or asymmetric bonds, it's mostly IR active, not Raman active.
Yes.
So for the non-symmetric classes of materials, is it all IR active or Raman?
No. There, a particular vibration or mode can be both IR and Raman active. That's the only example when it's really the presence of the center of symmetry forbids strictly. For all other materials, it's mixed with different intensities, but it's a mixture. We measure the reflectance under high magnetic fields, like. Yes, I measured the transmission, and there was an example somewhere for the, like that. I mean, so if, yeah, I understand now. The bore of the magnet is pretty small, right? So one has to somehow manage to install and we manage to a second light pipe, slightly bend the light, so light is reflected, goes back, and now the bolometer is here. So it's more difficult, yes, but doable.
First question here. I have one question on the detection side, where you have this. Can you please the slide with where you detect the light?
Not here.
More. Yes, yes. One, yes.
Yeah.
So is it no one more? Is it the position? So the detector is position sensitive, or it is energy sensitive in a sense?
It's position sensitive. It has, of course, its spectral response. But let's say for the ideal detector, it can be simply, especially modern CCDs, consider to have a flat response over, let's say, all visible light. And then it's position sensitive. It has to be calibrated. You use a calibrated source. You know that this X coordinate corresponds to this wavelength. And
So, but the resolution will not sit that high, like let's say the wavelength of light.
the resolution is a combination of few things. Of course, it's not that high. Even I think it does exist, resolution-limited spectrometers. It is a combination of things. Let's start here. Any detector has its size, real life. Standard modern CCD is 20 microns pixel width. And if you reduce it to 2 times, 4 times, the signal will decrease as a square of this. It's possible, just losing your signal. Let's say this is a 20 microns pixel. Then for the highest resolution, the slit should be also open to 20 microns. Because what's happening is like you reconstruct the image of the slit in the focal plane here. And then to achieve the required resolution is the focal length, the dispersion. You move it 10 times, 2 times further away, and that's you have big displacement.